We're now going to finish off the proof of the characterization of the polytope of the intersection of matroids. So the next, in the previous lecture, we saw some results about chains of tight sets corresponding to an element of the independent set polytope. Now we're going to start looking at the intersection of the two polytopes. So Lemma 3 says the following. I'm keeping the numbering system from the previous lecture because I want to refer back to those lemmas as well. It says the following. If X is now a vertex of the intersection of two independent set polytopes of matroids 1 and 2, then there are two chains, one which I'll denote by calligraphic or script C. These don't have to necessarily be the same size. And script D, so I'll write CK and DL and no assumed relationship between K and L, such that two properties hold. First, that, maybe I'll call this capital I, for any I, X of CI equals R1 of CI. In other words, the C's are tight with respect to R1. And again, everything is in reference to the particular point X that we're dealing with. And similarly for the D's. For any J, X of DJ is equal to R2 of DJ. Turns out that property is going to be quite easy. We're just going to basically build sets C and D in order to satisfy this. But we make no assumptions about their size or anything else. And the second assumption, which is really the main part of this result, says that if I look at the collection of vectors where S is an element of either one of these two chains, so S belongs to C or it belongs to D, this collection of vectors contains at least some number of linearly independent vectors. So this set of vectors, let me write this, let me clarify this. This is a set of vectors in RE. And this contains this many linearly independent vectors. This is an interesting proof because it really uses elements of linear algebra in a substantial way. So let's get to the proof. So the first part is straightforward because we construct it to be so. So in other words, given X that is a vertex, I won't repeat it, but let's keep that in mind. We're going to use that property. Given X a vertex, we can construct the chains C and D so that property 1 holds. In other words, construct inclusion-wise maximal chains, but given X. So we're not choosing X. So in other words, we just look at all of the tight constraints and we write out what C and D are. So the interesting part, therefore, is really this the second part that we need to show. Okay, so what is P of M1 intersection P of M2. We already have this characterization. The intersection of two polytopes is all the set of points that belong to both of them, which means that any set of points that satisfy simultaneously all of the constraints of one and all of the constraints of the other. And so this is indeed that first polytope that we wrote at the beginning of the previous lecture when we stated the main theorem. So this is the non-negative vectors x, so that x of u is less than or equal to r1 of u, and x of u is less than or equal to r2 of u, and this has to hold for every subset of my ground set. Well, this is a polytope, so if x is a vertex, then we know that there have to be at least, or exactly, E, cardinality of E, tight independent constraints. So it's a vertex. This implies that there are E tight and linearly independent constraints. And we're just going to find these. So some of them come from the non-negativity. How many of those? Well, we're relating this whole problem, this whole lemma 3 is about relating the number of independent sets to independent vectors to the cardinality of the support, and the complement of that is exactly the number of independent constraints we get from the positive orthant. So in other words, we know that E minus cardinality of the support of x, this is just how many components of x are equal to 0, this many come from this set of constraints, and therefore we have to find this many have to come from the other constraints. So they must come from linearly independent vectors chi t such that t is tight with respect to R1 or R2. Let me just clarify this point to make sure that we're all on board here. The constraint x of u, this is just shorthand for writing out what that uth row of the matrix, of the constraint matrix is. This is where we're looking for independent constraints. And what is that uth row? It is exactly the indicator function of u. So in other words, this is exactly the dot product between chi of u and the full vector x. It just picks out and sums all of the vectors, all of the elements of x corresponding to elements of u. And therefore, if we want to find tight constraints, this corresponds to this vector having to be independent for all the tight, for sets u that are tight. Okay. And now we're going to use the previous lemma, lemma 2. So the lemma 2 from the previous lecture tells us that, let's name this something, that S1, which I'm going to define as the span of chi C, such that C is in C. Well, the previous lecture, that lemma, told us that this set contains, the span contains any vector chi t such that t is tight for R1. In other words, any t such that x of t is equal to R1 of t. And similarly, I'll call this S2. This is going to be I'm going to call this the span of chi d, where d is in D. Similarly, this contains any chi t such that t is tight for R2. So I'll just write an S2 similarly. So that means that now let's look at the span of chi u, where u is in either C or D. Well, this span is certainly contains S1, and it certainly contains S2. So that means it contains their union. Again, remember that the union of the spans is always a subset of the span of the unions. So this is a superset of S1 union S2. But S1 union S2 contains this union contains all chi t such that t is tight for R1 or R2. So let's summarize. We've actually finished the proof of this lemma. We've said that by virtue of the fact that X is a vertex, we must have this many support of X, that many linearly independent vectors chi t, where t is tight either with respect to R1 or with respect to R2. So in other words, if I look at the full collection, if I look at all the vectors chi t, where t is tight with respect to R1 or R2, I know that that set has to have at least support X tight vectors. So I know that all of these are at least are independent, but then all of these are contained in S1 union S2, and these are in turn contained in the span. And that's exactly what the lemma was promising. So the conclusion is that the dimension of this term here on the left, the dimension of the span of chi u, where u is in C or in D, has to be greater than or equal to the number of linearly independent vectors in S1 union S2, which by virtue of the fact that X is an extreme point, is at least support X. And this is what what we wanted to prove. Okay, so now we have the basic tools in place so that we can prove the theorem by induction. So we prove the main result that this polytope by induction. And as with most of our proofs by induction on Matroids, we're going to use the two operations we have of deletion of an element and contraction of an element in order to use this. So let's assume that these sets are different, and let's let X. Or let's back up. So one inclusion is clear. So I'll just leave this as an exercise. It really is just making sure you understand the definitions. So the fact that this inclusion holds is straightforward. I'll just write it. It really just follows from the definitions. So this exercise is just to make sure that you have the definitions straight. So we're going to focus on the reverse inclusion. So for the other inclusion, let's take X. That's a vertex in the intersection of the independent set polytopes. Again, since everything here is a polytope, if
they're not equal, then the larger set has to have a vertex that's not included in the other set. So let's let X be such a vertex, but not in P of M1 intersection M2. Okay, so we're first going to use deletion. And we're going to use this in the event that some element of X is equal to 0. So if xi is equal to 0 for some I, again, what are we trying to show here? We're trying to show that xi is in the convex combination of common independent sets. So if xi is equal to 0 for some I, it's natural to think that we're going to use deletion, because any convex combination should be a convex combination of independent sets that don't use element I. So we could just delete it, and all the other constraints should be satisfied, and then be able to appeal to induction. So let's see the details, but this is how we should be thinking now, having been through a number of lectures on matroids. So if xi equals 0 for some I, delete to form the two matroids, M1 with I deleted and M2 with I deleted. And remember that the independent sets of a deletion are exactly the independent sets that didn't contain that element. And then we can also form an element x tilde that is, how shall I write it? That's basically x without the ith component. In other words, or sometimes people denote this by minus I. What I really mean, this is all the xi's, xi minus 1, xi plus 1, xe. I've just omitted that. I've omitted that element. So, well, what do we know? Then x tilde certainly satisfies all of the matroid constraints for M1 with I deleted or with I not deleted. It satisfies all of those constraints. So that means that X is in this polytope, but by the same argument, it's also in this polytope, and by induction, this is equal to this intersection is equal to the polytope of 2 minus I. So what does that mean? What does this final conclusion mean? It means that x tilde can be written as a convex combination of independent sets that in common independent sets for M1 with I deleted and M2 with I deleted. But then just by appending 0, we immediately see that, well, actually x, which again is just x tilde with 0 in the ith place, is also equal to that same convex combination of independent sets, but now just viewed as independent sets in the larger matroid, none of which happen to take that ith element. So in other words, it's we've got that, which is what we wanted to show. Okay, so now we're in the situation where our remaining situation is the case where none of the xi's is equal to 0. And in this case, one option is to use contraction if one of the xi's is equal to 1. So if xi is equal to 1 for some I, now let's think about what this means and why it's going to be natural to use contraction. Remember that from our previous lectures on matroids and those two operations, that in the contracted matroid, let me write this. So recall that I is an element of the independent set when I contract a particular element I, exactly when I plus I
is an independent set in the original matrix. And if xi is equal to 1, if we're hoping to decompose x as a convex combination of common independent sets, if xi is equal to 1, then I is going to be an element of every single one of those independent sets in that convex combination. And so again, this should be our frame of mind if we're thinking about using induction. If xi is equal to 0, deletion is natural. If xi is equal to 1, contraction is natural. So therefore, let's consider M1 with I contracted and M2 with I contracted. Now remember, I've written the definition above. The independent sets here are different. They're not the same as the deletion sets. And also, let's let x tilde be the same thing. Equal x minus I. I'm just removed that ith coordinate, which was equal to 1. So in that case, I know that for any subset of the ground set, excluding this ith element that I'm contracting, x tilde of u is equal to x of u plus I minus 1. Because x tilde, I just removed that ith coordinate, which was equal to 1. And this in turn is upper bounded by R1 of u plus I minus 1, which is equal to R of M1 contracted I of u. By definition. Remember, this is the definition of the rank function on the contracted matroid. And it's equal to the rank of the set minus the rank of that element, which in this case is 1, by virtue of the fact that x did belong indeed to the intersection of the two independent set matroids. And therefore it couldn't be that the rank of element I is equal to 0. So this implies that x tilde is an element of the independent set matroid for the contraction, because it satisfies all of these constraints. Right? This is exactly what this is saying. But it also satisfies this with respect. I could have replaced R1 with R2, and therefore it is also an element of P of M2 with I contracted. And by induction, this is equal to P of M1I intersection M2I intersection. So this means that x tilde can be written as a convex combination of common independent sets of the contracted matroid, common independent sets on the ground set E minus I. Again, lambda alpha is non-negative. Sum of lambda alpha equals 1. Now, we know that I alpha is an element of it's a common independent set. Sorry, there's a lot of notation here. So that means that it's simultaneously an element of I1 when I contract little I, and I2 when I contract little I. And exactly what this means, I wrote it up upstairs. This means that I alpha plus I is an element of I1 intersect I2. And now we see we're in business, because this tells us that x, which is equal to x tilde with that 1 put back, again, I'm being a little loose here with my notation. This is the ith position. here, this is indeed just equal to that a convex combination of chi, not of I alpha, but I alpha plus I, with that ith element put back. And so we conclude in this case that x is also in P of M1 intersect M2. We have one final case to consider. We used deletion if x had some coordinate that was equal to 0. We used contraction in the event that x had some element that was equal to 1. So we have just one final case to consider, and this is where we're going to use the lemmas. So now let's suppose that 0 is less than xi is less than 1 for any I. So now let's construct chains that are tight. So again, C is going to be the set C1 up to CK, and D the same thing. Oops, DL. And all of these are tight, right? Just by how I construct them. So that means that x of CI equals R1 of CI, and x of DJ is equal to R2 of DJ for every I and j. Now let's think about what these sets have to satisfy. So here's my set C, and well, what does this tightness tell us? Obviously, the rank is integral. So how can the rank be integral when it is made up of a sum of values that are non-integral, that are strictly between 0 and 1? Well, it must be that in between, these sets have to have at least 2 elements, because I'm adding these up in order to form, because the increments also have to be integral. So in other words, the cardinality of CI plus 1 minus CI better be at least 2. Again, just to make sure we're all on the same page here, imagine that C1 had 2 elements, and C2, which contained it, had 3 elements. And this wouldn't be possible, because we know that x of C1 has to be integral, and x of C2, which is just x of C1 plus x3 in this case, is also integral. And that could only happen if x3 were either 0 or 1, which we have ruled out. So we know that there are at least 2, possibly more, elements in each one of these, what we've called increment sets, for all I. And similarly, dj plus 1 minus dj also has to be at least 2 for every j. So how many elements are there in the set? What's the biggest k and l could be? Well, clearly that means that k and l is upper bounded by e over 2. Right? If we know that C1 contains at least 2 elements, C2 contains at least 4 elements, and so on, then I couldn't have a chain, and this is a chain, I couldn't have a chain of more than e over 2 elements. So now let's count independent sets. So we know by lemma 3 that the set Chi U, where U is any one of the C's or any one of the D's, we know how many independent vectors this contains. So this contains support of x independent vectors. But in this case, we know that the support of x is everything, so this is
equal to the cardinality of E. But if this contains that many independent vectors, how many vectors total are there in this set? Well, this set contains just k plus l vectors total. So if k plus l vectors total have to contain at least cardinality of E independent vectors, and k plus l has to be at least E. But if k and l are individually E over 2, well, that means that k has to equal l, which has to be equal to E over 2. But what does that mean? If you have E over 2 elements in your chain, and every time in every set adds at least 2 elements, then this implies that ck, the final element, is equal to E. Has to, because I augmented E over 2 times, and I added at least 2 elements each time, and I had a chain. And similarly, dl, which we know now L and K have to be equal, is also equal to E. But then we have a problem, because it is not possible now. So what does this tell us? This tells us that C and D have at most E minus 1 sets, because the last set, CK and DK, DL, we know L equals K, they have to be the same thing. They have to be the whole set. And now you see we have a problem. We contradict lemma 3, because there is no way that we can have E independent vectors out of a collection of E minus 1 independent vectors. So this is a contradiction, which finally we use to conclude the theorem. So this proves this characterization of Matroid intersection, the Matroid intersection polytope.